Okay, good morning. Hope you had a good weekend. Ready to get down to business?
First of all, sir, how was the cardio? How's the
Very good. It's going very good. Yes.
You better be running.
12 miles yesterday on my bike, and I think I've done at least 10 miles a day on my bike. So I've lost six and a half pounds already. So, but those are the easy ones. The ones in the beginning are always the easy ones. So
You track your fitness, sir, like with heart rate
Yes.
monitors, or you're
Yeah.
using a fitness watch?
I have a chest strap for my heart rate monitor.
Nice. I have one too. I just got one. I think it's
Yeah.
really cool.
What kind did you get?
It's the Garmin HMR Pro.
Okay. I use a thing called Wahoo. It's a bike computer, but
Oh,
you can also use it for, yeah, it tracks power and, like actual power into the pedals. And
right. Yeah,
so,
that's interesting.
yeah.
Y'all
Okay.
are gonna get me running again.
Hey, do it. Hey, that's it. Yeah. It's been hard. Yesterday, Super Bowl, I wanted to eat all the chips and crap that we had out, but I was very disciplined. It was hard. Okay, so last time we were talking about trig integrals. Oh, I should show you what we're doing today. Today, we're going to continue trig integrals. We're going to start trig substitution, hopefully, if we get to it. Next class is all trig substitution. Yep, that's where we are. Okay. So last time, oh, why'd I hit that button? Hold on, hit the wrong button. Okay, last time we were talking about integrals that involved sine and cosine. And we were talking about, if you have an odd number of sines or cosines, you can always factor one out and then make a substitution and use Pythagorean identities. And then if you had even powers of sine and cosine, we use this half angle identity, or the power reducing formulas right here, to kind of chip away at the powers on the sine and cosine. So if you did the homework on that one, if anyone actually went after that cosine to the sixth, it was, it's a pretty long problem.
I didn't get around to the 6-2 homework.
Yeah. So now what we're going to do is we're going to shift gears a little bit, and we're going to talk about integrating, doing integrals that involve secant and tangent. Now, there's certain things we need to know to start, all right? Just like we needed to know some things about sine and cosine, we need to know some things about secant and tangent. Namely, that the antiderivative of secant squared, right? The antiderivative of that is tangent. And also the antiderivative of secant tangent is secant. We need to remember that from Cal 1, right? Derivative of secant x is secant x tangent x. Derivative of tangent of x is secant squared x. So we need those. And then we need to kind of adjust those formulas to account for if we ever have some scalar in front of the x, the antiderivative of secant squared of ax would be 1 over a tangent ax. Again, scaling out the 1 over a. And then same thing for this one. Okay, that's what we need to know going in. Now, how do we deal with integrals that have secant and tangent? So there's a set of steps. There's a procedure, not steps. There's procedures for if you see certain things. So the main thing I want you to take from this, there's two cases we have here, is that in either case, we're going to be using a Pythagorean identity. But the identities we're using is this identity. There's actually two identities. This one, well, this one is the only one we really need. This one can be solved for secant squared. So we can say secant squared x is 1 plus tangent squared x, or we can say tangent squared x is secant squared x minus 1. All right, those are like the two versions of the Pythagorean identity we're going to use. And so the first technique says, look, if you got tangent and secant together, with the power on the secant being even, then you're going to do this. You're going to factor out a secant squared. Now, if you do an integral with secant and tangent, and you have the tangent raised to an odd power, you're going to factor out a secant x tangent x, and then use a Pythagorean identity. So let's just do some examples, and then hopefully you'll see how this is going to work out. So starting with this one, So I look here and I say, oh, hey, look, I've got tangent and secant together, and I've got secant to an even power, right? So that's going to allow me to rewrite this as tangent to the fourth x secant squared x times secant squared x dx. So I'm peeling off a secant squared from that even power of secant. This, I want to be thinking to myself, that secant squared is the derivative of tangent, right? That's what the derivative of tangent is. So I know that when I make a u substitution here, u is going to need to be tangent, and du will be equal to secant squared x dx, which is exactly what we have here, right? That matches up exactly. But that means that the rest of the integral needs to be written in terms of tangent, because that's my substitution. U is tangent. Well, I already have tangent to the fourth. The only thing I need to do is take this secant squared and somehow get that in terms of tangent x instead. That's where the Pythagorean identity comes from, right? The Pythagorean identity says, well, I'll go back to the notes. It says here that if you have secant squared x, right? Secant squared x is 1 plus tangent squared x. Okay, well, I can use that then. I can rewrite this as integral tangent to the fourth x. And then this in parentheses becomes 1 plus tangent squared x. That's what secant squared x is. And then this secant squared x, I do not change. Do y'all understand? I'm not changing this one to tangent. I'm leaving it there because that's the derivative of tangent, and I need it there for the substitution. Questions? Replace all your tangents with u's. U to the fourth, 1 plus u squared. And then this yellow part becomes my du. And now you've got a nice little polynomial here. I'll just distribute the u to the fourth through. Power rule. And then that's it. I've got my antiderivative, replace u with tangent, and we're done. 1/5 tangent to the fifth of x plus 1/7 tangent to the seventh x plus c. Questions? That was pretty clean, yes? Pretty clean?
Yeah.
No.
Hey, real fast.
Yeah.
With the exponents on like a tangent or any of the trig functions, does it matter if like the exponent is outside, or does it do you have to put it after like the in?
Okay, so yeah, so here's the thing. Tangent to the fifth x could be written tangent x in parentheses to the fifth, but it cannot be written tangent x to the fifth.
Because that would be x's to the fifth.
That would
the
imply,
tangent. Gotcha.
that would imply that the fifth power is only acting on the x.
Right. Coolness.
Got a question.
Yes.
So for when you did the u substitution using tangent x, what caused you to use tangent instead of secant, for example?
Okay, so if I would have done u is equal to secant x tangent, I'm sorry, secant x, right? Then the derivative of that is secant x tangent x dx, right?
Yeah.
Okay, so going back to this original problem, what I would have to have done is to see my du, to actually see that secant x tangent x dx there, I would have to peel one of the tangents off, peel one of the secants off, and then write it as secant x tangent x dx. Do you see that? All I'm doing
Yeah,
is
I see it. Yeah, because if
Okay.
you use if you use tangent x, okay, yeah, I'm following.
You're okay with that? So do you see
Yeah,
why
yeah,
this?
yeah.
why
You
it
just
won't
divided
work?
the secant squared out when you did you.
But do you see why I can't do this way?
Yes.
The whole thing is we need to rewrite everything in terms of secant, everything except the yellow. The yellow I don't need to worry about, but the rest of it has to be in terms of secant. So that's secant already, that's good. But now I've got to get tangent cubed in terms of secant, but I can't use the Pythagorean identity because it's an odd power. I would have to
Oh.
have like tangent squared or tangent to the fourth or something like that. Then I can use Pythagorean.
Why
Make
do you
sense?
have to write it in terms of secant specifically?
Why do I? Because I need to make the u substitution, right? Like this would become u cubed. This is the derivative of u. And then now this needs to be somehow in terms of u. Because you need your whole integral to have only one variable in it, u. So everything has to be switched over in terms of u, which these two can get switched over easily. This one, I have no clear path to take me from tangent cubed to something with secant in it instead.
Okay, thank you.
That makes sense to everyone? Good question. All right, so the next one that we're gonna do is this one. Tangent to the fifth, secant to the third. This is gonna be an exact illustration of the other scenario, which is, see, I don't have secant to an even power, right? And according to these steps, if I do have an odd power on the tangent, right, with an odd power on the tangent, then what I'm going to do is factor out a secant x tangent x. So I'm going to pull one of the tangents off. I'm going to pull one of the secants off and place it over here as a secant x tangent x dx. And this piece right here becomes, I know that that's the derivative of secant. So my substitution will be u is secant x. The derivative is secant x tangent x dx. This right here is matched up perfectly. And so now I need to get everything in terms of secant. Well, the secant squared is good, right? That's just in terms of u squared, but tangent now needs to be in terms of secant. So now I can go to the Pythagorean identity again because it's an even power of tangent. So I can rewrite that as tangent squared x squared, secant squared x, secant x, tangent x dx. That's the part that matched my du. Now tangent squared, I need the Pythagorean identity for that. So the identity says that tangent squared becomes secant squared x minus 1 and then squared, and then secant squared x, and then your secant x tangent x dx. Making sense? Yeah. Now everything is in terms of u. So my new integral, I'm going to just squeeze it in here. My new integral is parentheses u squared minus 1, then that squared, then times u squared, and then du. So u squared minus 1, all that squared, then this is u again squared. I'm going to expand out the first one. So this is u to the fourth minus 2u squared plus 1. Still have to hit that with the u squared. So I just did this in my head, u squared minus 1 times u squared minus 1, and FOILed and collected like terms. And then I'm going to distribute that u squared through. So I'll have a nice polynomial here in u. And now power rule. I can just do term by term. So the antiderivative of that would be 1/7 u to the 7th minus 2/5 u to the 5th plus 1/3 u to the 3rd plus c. And then just replace all the u's with secant x. So secant 7th power x minus 2/5 secant to the 5th x plus 1/3 secant cubed x plus c. Questions? Secant to an even power, pull a secant squared out. Tangent to an odd power, pull a secant tangent out. All right, two different methods.
You know, what I will say is, I don't know if I'd say these are easier or harder as of yet than integrating by parts, but they take up a hell of a lot less space.
Yeah, I think these are, especially secant tangent is pretty straightforward with these two examples. So let's move on. So there are other cases where you have maybe secants and tangents or sines and cosines. So we're just kind of like, we've got the two main ideas. We know how to deal with sine and cosines together. We know how to deal with secants and tangents together. Now, there's some other situations where things are not as obvious. Sometimes we'll need knowledge from common identities. Sometimes we'll need integration by parts. And sometimes we just need persistence. All right, so a couple of examples. First one, tangent. I believe I did this one already. I feel like I did this last class at the end. Let's see. Yeah, I did this one in class last time. I'll just walk us through it again. You're trying to find the antiderivative of tangent. Don't say it's secant squared because that's the derivative, right? We want the antiderivative of tangent. So I rewrite it as sine over cosine, and then I just did a basic U substitution. And I wound up getting at the end of this natural log. Yeah, remember I got this and it didn't match the formula sheet. So then I had to show you how it's just a property of logs. So I've done this one. I'm not going to redo it. And then the next one I want to do is this one, secant x. The antiderivative of secant. So this one done last time. All right, this one, okay. Prepare to be amazed. Right, there's no easy way to do this one. Like in terms of like, even if you try and rewrite this as 1 over cosine x, right? That's what secant x is. There's no U substitution you're going to do. There's nothing in those strategies for sine and cosine that we learned last class. There's nothing we can do because you can't peel anything off and can't use a Pythagorean identity. This is an extremely difficult integral. All right. So I'm going to show you how it's done. And then I think what you're going to see once I show it to you, you're going to appreciate that the way that mathematicians think. All right. Somebody had to sit with this problem for a long time and figure out to do this to make it work. All right. I don't know how long it took them to figure this out. Could be years of their life. I don't know. But this is the way you can do this one. You ready? I would never expect that you come up with this on your own. Okay. Just watch. So what I'm going to do is this. I'm going to take this integral, secant x, and I'm going to multiply it by 1. Okay. I mean, we can always multiply anything by 1, right? So if I do this, then I can choose how to write that 1, right? 1 can be anything over itself, right? Anything over itself. So here's what I'm going to use, and it's going to be like, what the hell? Why are you doing that? I'm going to do secant x plus tangent x over itself. Secant x plus tangent x. Okay. Dx. So that's the one I came up with. All right.
Oh, that's awful.
Yeah, like why would you ever do that? So watch what happens. This is pretty freaking awesome. Distribute the secant through, okay? And you get secant squared x plus secant x tangent x. Do y'all agree that's what I get on top? Yeah. Over the bottom, which is secant x plus tangent x. Again, like why in the world would you ever think to do that? Does anyone see why?
Yeah, because we've got a U substitution now.
What's the U substitution?
Well, we've got secant and secant x tangent x. I guess we also do have secant squared and tangent, so we could do that too.
How do you mean? This problem has now become a simple,
Yeah,
very simple U substitution. What is the U?
Is it secant?
Not secant. Who sees it?
Is it secant x plus tangent x?
It's the whole denominator. It's the whole denominator. Watch, secant x plus tangent x. Now, what's the derivative of that? So the derivative of that, well, what's derivative of secant x? Secant x tangent x, right? Plus what's derivative of tangent x?
Secant squared x.
Secant squared x. Do you have that?
Yes. On the
Yeah, that's what the numerator is. The entire numerator is the derivative of the denominator. Miraculously, right? No, it's because someone figured out this is the way it'll work. All right. So again, I can't stress this enough. How somebody came up with that one right there was by persistence, and they finally figured out, hey, this works, right? This works. So that means I can rewrite this integral. What does this new integral become? Remember, all of
over
this
u.
right here. Yeah, it's just, that's all du, right? That's all du. And then that's a u on the bottom. So that, isn't this just 1 over u du? And the antiderivative of that is natural log. So natural log of the absolute value of u plus c. And now replace the u with secant x plus tangent x plus c. Pretty crazy, huh? That one.
That one was an interesting one, I gotta say.
Yeah, so I mean, I would never expect anyone to come up with that. You just, now that you've seen it, you're like, wow, okay, yeah, that's pretty, whatever you want to say. Pretty
So I was
whatever.
gonna say, is that on a formula sheet somewhere?
It is.
Oh,
So
good.
now look, if you look at our formulas, all right, these are our basic integral formulas from our formula sheets. I want you to now pay attention to the fact that following this kind of idea, we now know the antiderivatives of all the trig functions from pre-cal. We already knew today the antiderivative of sine, the antiderivative of cosine, right? The problem I did last time was tangent, right? The last time I did is tangent, and I just did this one, secant, didn't I? Yes. So I'm not going to show you the others, but just you'll have to trust that there are ways that you can get, where is it? Where's just secant? Hold on. Do they have, I mean, just cosecant. So here's cosecant, right, by itself, and cotangent. Those are the 6 trig functions from pre-cal. Sine, cosine, tangent, and their reciprocals, right? Secant, cosecant, cotangent. The formula sheet contains all of the antiderivatives for those. I have proven to you, well, this we knew from Cal 1, this we knew from Cal 1. This I just proved to you. This I showed you last class. So these two I'm not showing you, you just have to trust that that's what they would be, okay? Trust that it could be shown.
What is the association with natural log and trig functions?
Say again?
What is the association of natural logs and trig functions?
What's the association of them? What do you mean?
Yeah, so why is the integral natural log of the absolute?
I mean, for the trig functions, for those trig functions, why is it natural log?
Or just in general, like why is natural log so involved in the integral of?
Because the derivative, think about what the derivative of natural log of something is, right? The derivative of the natural log of something is basically the derivative of that something. Whatever's in the natural log, it's the derivative of it divided by itself, right? Go back and look at, I think this one, you know what, we'll do this one. That one is, let's do cotangent just to show you. Maybe it'll help you make the connection. If you want to do the integral of cotangent x, right? Dx. Cotangent by definition is the reciprocal of tangent. So instead of sine over cosine, it's cosine over sine, right? Dx. So I'm asking basically this question. right? Like what do I take the derivative of to get this, right? What do I take derivative of to get this? Well, notice that the numerator, right? That numerator is the derivative, I'll write it this way. This is the derivative of that denominator, isn't it? The denominator is sine, and the numerator is the derivative of that. Well, that's the way the natural log works, right? If you take the natural log of u, let's say, and you take its derivative in Cal 1, you get 1 over u times the derivative of the u itself, u prime, which is u prime over u. In other words, the natural log is very nice at spitting out a ratio of a derivative over the original function. And so that's why it comes up as the antiderivative of a lot of trig functions, because a lot of these trig functions are ratios of sines and cosines, which are connected to each other through derivatives. I hope that makes sense.
Yeah, so you're saying that ratios, so when it's like a natural log is like a ratio that works well with other ratios.
Natural log, the derivative of natural log creates a
Because
ratio.
Because
right?
natural log is already a ratio, it's a simpler version of a ratio that is easy to like conceptually realize the derivative of. That's why other ratios kind of follow that same format. Is that what you're trying to
The
say?
derivative, though, natural log by itself isn't really a ratio. I mean, you could always say natural log over 1 is a ratio, but the natural log function is, from college algebra, we know natural log looks like this, right? Okay, that's the function. What I'm saying is that the derivative of it always creates a ratio, right? When you take derivative of natural log of u, you always get this ratio from it that has the derivative on top and then the original function on the bottom. And so anytime we're talking about trig functions that involve sine and cosine, since sine and cosine are derivatives of one another within a scalar, right? Derivative of sine is cosine, derivative of cosine is negative sine. So they are connected to each other. Anytime we have a trig function that involves sine and cosines, we're going to have a ratio of sine and its derivative or cosine its derivative. So we should expect that the antiderivative of something like that should involve a natural log. Okay, let's move to the next one. There's the other answer to that question is, just that's just the way it is, like that's just the way it works. Like, can't really explain why it is always that way. I mean, there are just certain things that are just mathematical truths, and that's the way it is. Look at this one. This one's secant cubed, okay? This one's secant cubed. So in our little thing here for today, I told you how to deal with when you had tangent and secant together. And I said, if you see the secant with an even power, right? If I said an even power, then you're going to do something. Well, here we have secant with an odd power. And I have not given you any indication as to what to do with that. The second part of this says what you do if you have tangent to an odd power. Tangent to an odd. We don't have tangent to an odd, we have secant to an odd. So here's what I'm gonna do. All right, this again is just to show you how, even though we kind of know a general idea of how to go about these problems, you could get something like this that doesn't fall into either one, but we can still do this one. So the way to do this one is to rewrite this as secant squared x times secant x dx. So we just peel it apart, okay? I have 3 secants being multiplied together, so I'm going to write it as 2 secants being multiplied together and then 1 secant. And the reason I'm doing that is because now I can do integration by parts. And what I'm going to do is I'm going to choose my u to be the single secant that I have, and the dv to be the secant squared. Why do you think I pulled? Why do you think I'm letting the dv be secant squared?
Turns into tangents.
Yeah, because the antiderivative is tangent, right? So that's why I did that. So I'm going to differentiate over here. The derivative of secant x is secant x tangent x dx. And then the antiderivative of secant squared is tangent x. Now, right now, there's no clear indication whether or not this is going to work. Okay, I'm just trying this. Go with me? Here we go. This becomes ultraviolet, these two multiplied, secant x, tangent x, minus the integral, and now I'm going to multiply the diagonals, these two together, right? So when I multiply those two together, I'm going to have a tangent squared, right? And then a secant. So tangent squared x secant x dx. And now we're still stuck. Because when I'm here, this doesn't fall into either of these, right? This is what you do when secant is even. This is what you do when tangent is odd. And so for this, I have tangent even, secant odd. So I can't follow that format from before, right? So what am I going to do? What am I going to do? Well, sometimes I just got to show you how to go about something, and it kind of opens your mind up, and you're like, oh, okay, I didn't realize I could think about it that way. So here's what I'm going to do. I'm going to rewrite the tangent squared as secant squared x minus 1, and then times secant x. So I'm just using a Pythagorean identity to rewrite tangent squared. Y'all agree with that? That's what tangent squared is. Does anyone see what's going to happen yet?
Yeah, you can distribute and then subtract.
So when I distribute that, I get a secant cubed x minus secant x dx, right? That's what I get. And because what? Because these two things, right? These two things, I'm subtracting this integral. I could split this into two integrals. The key is to see we have the integral of secant cubed. Do y'all see we have that in there? And that's actually what we're trying to find. This is kind of like that rabbit out of the hat problem I showed you with integration by parts, where what we were looking for appeared on the other side of the equation. We had to move it around. Same exact thing is about to happen. So what I'm going to do now is I'm going to go ahead and bring down the original left side of the equation. Okay, the left side of the equation, the original thing we're trying to find is the integral of secant cubed, x dx. And so far we have that it is equal to secant x tangent x minus the first integral secant cubed x dx plus this next integral secant x dx. So I split these two, right? I split this into two integrals, and I was very careful to make sure that my minus sign went through and made this a minus integral and a plus integral. Questions? So what we do now is just add, right? Add this integral to both sides. Add that over here. It goes away. And on the left side, I have two of them now, right? I have two of these integrals is equal to secant x tangent x plus, right? This is gone. Hey, wait a minute, antiderivative of secant x, right? We just did that. Do you have a formula for it? You could just look it up in your formula sheet, but we just did that.
Yeah, it's natural log secant x plus tangent x.
Yep, so that's that plus c. And I guess there's one more step. You got to get rid of this 2 over here, right? So you just multiply both sides by a half or divide both sides by 2, however you want to look at it. So my next line would be this line. Take that 2 out of there. I'll just squeeze a 1/2 in here. 1/2, 1/2. And then I don't need to do half of c because it's still a constant. So there you go.
Hey, question. Would you, like on a test or something, if something like this came up, which I'm sure it will eventually, would you prefer it to be put in that format there of a 1/2 times everything individually, or just put the whole thing over a 2?
Either way.
Because that's what I've been doing when I encounter these, like
Yeah,
on homework.
no, you could just do the whole thing divided by 2. It's fine.
Cool.
Okay, so, you know, just be aware that, you know, not everything is cookie cutter, right? It's not, this isn't just like I said in the beginning of the class, you know, Cal 1 is very mechanical, right? You have power rule, product rule, quotient rule, chain rule. Once you understand the rules and how they work, there's not a whole lot of mystery to things. But a problem like this, there's a lot of mystery because there's no like just, oh, I just do this, right? You say, okay, I've got secant cube, you know, what can I do? You know, what's going to direct you to split it, right? I don't know what's going to make you do that other than the fact that you've seen me do that before. Now you know you can try that on certain problems, right? So because there's no clear path, you know, it gets really challenging, right? All right, we are done with trig integrals, which is the first half of this section. And now we're ready to start the second half of this section, which is called trigonometric substitution. All right. You ready?
Let's do it.
All right. So this is where we want to, you know, have a little Zen moment or whatever. Things are going to get weird right now. So you know how when we've been doing U substitutions, the basic U substitution, when we first learned it, we were looking at the integral and we were like, okay, if I see something in its derivative, I'll make this substitution, right? And the whole idea was to make the problem that was real ugly look better, okay? Like look like something you can integrate. Here, this new idea of trigonometric substitution, okay, this new idea has to do with trying to handle integrals that involve one of three things. You're either going to have, I'm just going to write them down here. Hold on, let me see if I have a summary of all. So you're, yeah, let me do it. Okay, I'll just do it on my notes. So trigonometric substitution, which I'll just call trig sub, okay? Trig sub is when you have integrals involving the square root of some number minus x squared or the square root of x squared minus some number squared or the square root of x squared plus some number squared. This whole concept of trig sub is when you're looking at an integral and you see one of these three things in there. Let me give you an example of each of these underneath. An example of this would be square root of 4 minus x squared. Example of this would be square root of x squared minus 4. Example of this would be square root of x squared plus 4. All right. Now let's look at the first two. The only difference between these two is the order, right? The order. So we know with subtraction order matters. And there's nothing you can do to make this one on the left look like the one on the right. You cannot do it. I know you might want to say, oh, I'll factor a negative out and make it negative 4 plus x squared. And that's really negative x squared minus 4. And I will agree with you on that. But these two are not the same thing because you cannot pull that negative out of the root. You can't get it out of there. Do you all understand that? Because you can't take square root of negative 1. So that negative is in there. So these two will never, ever, ever, ever be the same thing, okay? They won't. So those are distinct expressions. This one and this one are distinct from one another. Now the last one, x squared plus 4, you could switch the order and it would be the same expression, all right? X squared plus 4 is the same as 4 plus x squared underneath the root, right? Those are the same. So these two are equal to one another. So when we say there's three cases, it's either this one, right, where you have some constant minus the variable squared, or this one where you have the variable squared minus the constant, or this one where it doesn't matter. You just have variable squared, constant, and it doesn't matter if it's plus, you know, which one is first. Trig sub is a technique that we use to attack any integral that has these expressions in them. All right. Got it? But the substitution we're gonna make is weird, okay? Because normally what we've done is we've looked at an integral, we've looked at it, we're sitting there, we're looking at it, and we say, oh, we're gonna let u be something, right? That's what substitution has normally been for us, right? Is we replace something complicated with u, right? We start with a complicated thing and we replace something complicated with just a single variable. Trig sub is different. We're going to take something simple and replace it with something complicated. And it's actually going to make the problem work out. Okay. So let's just hit the ground. I'm going to give you an example. All right. And there's a bunch of steps and techniques and everything else, but let's just go with the first example. All right, here we go. All right, so I look at this, and now's when you really start to feel the weight of this class, because you've got a lot of things now on your plate, right? You've got basic U substitution. You've got integration by parts, right? Now you've got this, well, we have trig integrals also, but right now this doesn't have sine or cosine or tangent or secant or anything, so I'm not really thinking trig integral. But now I've got this thing called trigonometric substitution. And trigonometric substitution is when we see one of those three things. And I see one of those three things here, right? I see that square root of 16 minus x squared, right? Which looks a lot like this generic formula, right? That's like the generic version, right? That's the generic version of that expression. And so for us in this expression, this really is like 4 squared minus x squared underneath the root. So this is like the a, right? The a is 4, right? Now I have to look and make sure there's nothing I can do with this. I can't do u sub, all right? Well, actually you could, but we're not going to. It's kind of complicated. I see that square root. I'm thinking trig sub, trig sub. Okay, so what the hell is trig sub, right? I see it. There it is. I'm thinking trig sub. Trig sub. Let's do it. Okay, but what is it? Well, here's what trig sub is. If you see, go back up to the notes here. Okay, if you see this, here's the general idea. If your integrand involves an expression square root of a squared minus x squared, then we are going to make the following substitution. We are going to replace x with a sine theta. We're going to replace x with a sine theta. Okay, so let's go back here. So I have the expression, right? Here's my expression. Square root 16 minus x squared. Okay, so that's telling me that I need to use trig sub. That looks like a squared minus x squared. So here comes the substitution. I'm going to let the x be equal to a sine theta. And what did we say that a was for this problem?
It's 4.
4. So I'm going to let x be 4 sine theta. Okay, so think about this. Think about what I'm going to do here. In this expression, everywhere I see an x, I'm going to replace it with 4 sine theta. I'm going to place that x with 4 sine theta, place that x with 4 sine theta, and then I need to get my dx to become something. Because do y'all see, if I replace the x's with 4 sine theta, now everything has thetas in it, right? Theta is a variable. So I need the entire integral to have thetas. I can't have any more x's, including dx, can't have it.
So d theta.
So we're going to, well, we can't just replace dx with d theta. What we need to do is figure out what is dx. So this was my substitution, right? I made this substitution, x is 4 sine theta. Now let's go ahead and take the derivative of it. The derivative of this would be 4 cosine theta d theta. Does that make sense? So I'm going to replace all my x's with 4 sine theta. I'm going to replace all my, well, the dx with 4 cosine. Hold on, did I say that right? Replace all the x's with 4 sine theta. I'm going to replace the dx with 4 cosine theta d theta. Understand? Now the question is, why the are we doing this, right? Like, what the hell, what is this all about, right? Like, this is nuts. We're replacing X, which is just X, with something complicated. Here's why we're doing it, right? Here's why. Watch this. If I take this expression, okay? Take that generic expression, or that, not the generic one, take that specific expression for this problem. And I want you to see what would happen if you replace the X with 4 sine theta. We would get 16 minus, and then I'm going to do 4 sine theta squared, right? That's what would happen. Now keep going. This is now 16 minus, now I have to square this. So I have to square the 4, that becomes 16, and square the sine, that becomes sine squared theta. They both have a 16, so I can pull a 16 out, be left with 1 minus sine squared theta. Wait a minute, 1 minus sine squared theta is
Secant squared.
Isn't it
Cosine
cosine
squared.
squared?
Cosine squared.
cosine squared theta. Pythagorean identity. So this becomes 16 cosine squared theta. And wait a minute, now I no longer have 2 terms, I just have 1 term. And so I can take the square root of the whole thing, and it just becomes 4 cosine theta. And that would have worked for anything, any generic form. Watch. Come back over here to this generic form right here. Replace X with a sine theta, okay? And rewrite this. I would get square root, the a squared's a squared, minus, now replace this X right here with a sine theta, and you're gonna get a squared sine squared theta, right? You square the a and the sine, and then they both have a squared, right? So I pull out an a squared, and as soon as I pull out that a squared, I've got the 1 minus sine squared. And then that 1 minus sine squared turns into a cosine squared. And now I can take the square root of each one, so I get a cosine theta. Every time that will happen. All right? Every single time you ever have a square root of a number squared, oops. Look over here. I'm saying every time you ever have the square root of a number squared minus x squared, if you make the substitution x is equal to a sine theta, then that entire square root thing will turn into the simple expression a cosine theta. Every time.
I have a question, sir.
Yes.
So if a squared, like say for example, 16 is no longer 16, it's like let's say it's 15. Instead of it just being a at the finish line, it'll just be the square root of 15.
That's right.
Okay.
If this number is not a perfect square, like first example, I use 16 because it's a perfect square, and so we can say a is 4. But if it was 15, well, then a would be the square root of 15. Okay, I mean, it's not a number we know, like the number 4, but it still is just a number.
The fact that it's a constant lets us just put it in that state,
That's right.
because
Yep.
you could put that in your calculator and it sure is a number, I'm sure.
Exactly. Okay, so here we go. We are ready now. We are ready to rewrite this integral. You ready for this? I'm going to rewrite this integral. I'm going to replace my x's with 4 sine theta, and the entire square root thing turns into what? This whole square root thing turns into
4 cosine theta.
4 cosine
4
theta.
cosine theta. I don't even need to really think about that, but let's just go ahead and do this. All right, so integral, the x becomes 4 sine theta, so I've got 4 sine theta cubed, right? That's x cubed. The whole square root of all this crap, I already did all that work here. That's just 4 cosine theta. And do not forget that dx becomes 4 cosine theta d theta. All right, so 4 cosine theta d theta is the dx. The square root of all this crap is the 4 cosine theta. And then the x cubed is this piece here. Okay. You all got that? let's do this. 4 to the 5th power on the outside of the integral. Because I'm going to do 4 cubed, then I have another 4, then another 4. So I have 4 to the 5th power. I'm going to pull it out of the integral. Then I have sine cubed theta, cosine squared theta, d theta. I had 3 powers of sine, and then cosine times cosine is cosine squared. Got it? What are you looking at now? What is this?
You can pull a sine.
Yeah, so we're back to the previous part of this section now, right? This is a trig integral. You got sines and cosines mixed together. You got to figure out, oh, we've got an odd number on the sine, so I'm going to peel off a sine. You see? So now we're back to what we did earlier in the section. So let's do it. Let's keep going. I'm going to go ahead and just bring this down.
I'm a little confused, sir. So whenever the end, is it gonna be? And because it's gonna be a trigonometric function at the end, right? So how does that relate to it being x cubed, the square root of?
Oh yeah, we got to get our answer back to X. Stay tuned. We got a long way to go still. Yeah.
Okay.
Yep.
Sorry.
So here we go. We've got this integral. We're going to pull one of the signs out, make it sine squared theta, cosine squared theta. Then we pulled one of the signs off to the side, right? And because of that, this is going to be our like du, isn't it? We're going to make a substitution. We're going to have to let u be what? If that,
Negative cosine?
well, we can use, why don't we just use cosine, and then when we get the derivative of that, we'll have negative sign, but we'll just scale it. How about that?
Yes, yes.
Okay, so we're gonna let u be cosine theta, right? U is cosine theta. And then the derivative of that we know is negative sine theta d theta, which we almost have, right? We're off by a sign. So I'm going to multiply both sides by -1, so it'll make this side negative, this side positive. And now this matches, right? These match, which means I need the rest of the integral in terms of what?
Cosine.
Cosine, right? I know this cosine squared theta can be replaced with the u squared. This can be replaced with negative du. And the sine
Sine.
squared still needs to be dealt with. So what now?
The Pythagorean identity,
Pythagorean,
which should
right?
be
1
the
minus cosine
1
squared.
minus cosine, yeah.
Yep, 1 minus cosine squared. At this point, we can do our u substitution. So I still have the 4 to the 5th integral 1 minus u squared negative du. Who has questions? We're not done yet, right? We're not done.
No, not done.
Okay, so I'm going to distribute the u through, right? So I have 4 to the 5th integral. I've got to do u squared minus u to the 4th du. Hey, let me pull this negative here in front of the du. Let me pull it out in front with the 4 to the 5th. So negative 4 to the 5th. And then that, oh, you know what? Another thing you could do is you could take that negative and distribute it through here and then change the order, make it u to the 4th minus 2. Either way, it doesn't matter. I'll just keep it like this. All right, I'm ready for the antiderivative. Negative 4 to the 5th. Okay, antiderivative. 1/3 u cubed minus 1/5 u to the 5th plus c. What was u?
Cosine theta.
It was cosine theta, right? Up here, here's what u was, cosine theta. So this is 1/3 cosine cube theta minus 1/5 cosine to the 5th theta plus c. Questions? Still not there. We're almost
Yeah,
there.
how do we substitute back in, I guess,
Yeah.
our X?
Yeah, so how do we get this back to X, right? We've got the antiderivative finally, right? We're there. We got to get it all the way back to X because the original, look at the original problem, it had X's, right? So in the very beginning of this class, I think it was the first day, might have been the first day. Reference triangles. Remember this reference triangle? I said this will come up again. Okay, it's time. It's reference triangle time. So what I'm going to do to complete this problem is I'm going to go all the way back up to the top to where we made the trig sub, which is right here. That's where we made our trig sub, right? That was the trig sub that we made. Right? That was what we did. Replaced X with 4 sine theta. What I'm going to do is I'm going to take that trig sub down here with my work. Back down here where I'm working here. And it was X is equal to 4 sine theta, right? That was my trigonometric substitution I made. Now what I'm going to do is I'm going to divide both sides by 4 to get an expression for sine theta. Right? I now have a connection between X and theta, don't I? I'm going to create a right triangle. I'm going to call this angle theta. And then sine, by definition, is opposite over hypotenuse. So this side is X and this side is 4. Does this look familiar? I mean, it's been a while, but doing this. Now, what are we interested in? Look at our integral. We want to know what cosine of theta is, right? That's what we want to know. What's cosine theta? What's cosine theta in terms of X? Well, we have a triangle. Cosine is adjacent over hypotenuse. So I just need to know this adjacent side, which you could solve for because you have the other sides of the triangle, right? Do I need to show this, or does everyone know that they know how to get this? Is everyone good at being able to get this adjacent side? Trusting, yes, no? Do a squared plus b squared is c squared and then just solve for this side?
Yeah,
Done it?
shouldn't you square the 4 though?
Oh, yeah, hold on. It was square root, yes, thank you. Pay attention, that should be a squared minus the x squared. So it's this side squared minus this side squared, square root.
But isn't that already what we got on our previous?
Say again?
Isn't that already what we got? Because our first sub.
Like,
Isn't
we-
it already?
Isn't that the beginning of the problem, is what he means, I think?
Yes, right, where was it? This thing right here, right? Earlier, is that what you're saying, that this is this?
Yeah.
That you could see here that 4 cosine theta was equal to that? That's what you're saying, right? Yes, we could have done that without doing the reference triangle, okay, for this problem. Generally speaking, though, it won't always be that way. So you have to be comfortable with the reference triangle because it might be asking, we might be at the end here and it's asking for something like cotangent or something, it could be secant. So it could be, there's a lot of things. The reference triangle is the best way to have all the information you need. Okay, so reference triangle, now cosine we can get here. So I think we're ready. This is going to be -4 to the 5th power, 1/3. Okay, so we've got to take cosine of theta. What is cosine theta? Well, off this triangle, it's adjacent over hypotenuse. So square root of 16 minus x squared over 4. But all of that needs to be cubed, right? That's what cosine cubed means. And then minus 1/5, and then cosine again to the 5th, square root of 16 minus x squared over 4, but all of that to the 5th power, all of that plus c.
Well, that seemed pretty fun.
Yeah, that's our answer.
So the test will just be one question.
Yeah, right.
Beyond that,
Yeah, right. So like theoretically, and I mean, this is the way it actually works on a test, I'm probably not gonna ask you any trig sub problems. Like just by themselves, right? Trig sub, like what we were doing last class. Because I can give you, sorry, not gonna ask you any trig integral problems, what we were doing previously. I just ask you a trig sub problem and you'll have to do a trig integral. Like you'll have no choice.
Are there problems where it requires every single step? Like somewhere in there where you use U sub, then trig, and then
Integration by parts.
Yeah,
Yeah.
I would like to practice one of those. Do you
Yeah,
have-
that's the baby steps into that. I'm not ready for that. But yes, you can start to appreciate the complexity. These things start to get very complex, right? And we haven't even had to do like any algebra. Like the square root was just sitting there staring at us. Like sometimes it's not staring at us. Okay, that's what you do if you have the square root of a squared minus x squared. You make the substitution a is equal to, let's say that again together. Let me scroll down. So in summary of this, if we have the square root of a squared minus x squared, we're going to make this substitution x is a sine theta. The square root thing is going to turn into a cosine theta, and the derivative of x will turn into a cosine theta d theta. Every single time, that's what happens if you start with the square root of a squared minus x squared. Okay?
And there's
And then I
something
just-
unique for the other two, isn't there?
Yep, and for the other two, it's a different substitution. The other two have different substitutions. So let's do this one. In my experience, trigonometric substitution, what we're doing right now, and the next section are kind of like the peak, the pinnacle of difficulty in terms of integration. Because there's so much you have to keep track of.
So
These
this is
problems
the
get very
hardest.
long and drawn out.
So this will be the hardest, like section is like the middle.
I think this section, the next one, yep. Yeah, we're
Yeah,
almost
what's
at the
the-
end
what-
of our techniques.
Wait, what's the next section?
Partial fraction decomposition. Which is a topic from college algebra pre-cal, but now we need to use it for integration.
Yeah, I know the term. I don't remember exactly what it means, but I don't remember it being happy.
Yeah, so
Same.
yeah, when we get ready to do it, I'm gonna ask you to go review it because we can't spend too much time going over how to do it. All right, let's focus on this one. Okay, so we look at this and we say, oh, look, I see this square root of x squared plus 9. Now, I have to make sure this can't be done with some easy substitution, right? Not trig sub, but just like our first way of doing integrals. I have to rule all that out first, right? So like if this x squared wasn't here and up top I had an x, I would do a basic u sub, right? I'd let u be x squared plus 9, the derivative is up here, I'm off by a constant. Okay, if that's what I had, I don't have that though. This is what I have. So I'm going to do a trig sub because I see the square root of x squared plus 9, which the generic form for this is a squared plus x squared. Here for us, the a would be what?
3.
3, right? A would be 3. Now the question is, what do you do when you have this? It's a different trig sub. So let's go look at the notes. So if you have a plus, where it is, the second one right here, I'm going to copy it right here. Oh no, why did I hit that button? Okay, so here's what we do if we have a plus there. I guess I'm just put it there. Okay. So if the integrand contains a square root of a squared plus x squared, we will use the following substitution. X will be equal to a tangent theta. A tan theta. All right, let's do it. So y'all told me already that A was 3, right? So X is gonna be 3 tan theta. The next thing I'm gonna do is just take the derivative. The derivative of this is 3 secant squared theta d theta. Okay? Y'all agree with that? Derivative of 3 tangent theta is 3 secant squared theta d theta. That's basically the top part and bottom part of this little formula box. The real question is, what does this ugly complicated thing turn into? Well, if we replace the X with 3 tan theta, it becomes 9 tan squared theta plus 9. And do you see we're going to play a similar game here? Replacing that X with 3 tan theta, you square the 3, you square the tangent, you get 9 tangent squared theta plus 9. You factor 9 out. And then what's tangent squared theta plus 1?
Isn't it just secant squared theta?
Secant squared, yeah. So that's 9 secant squared theta. And when you take the square root of both of those, you get 3 secant theta. So all my x's get replaced with 3 tan theta. The dx gets replaced with that. And this whole square root thing, right, gets replaced with 3 secant theta. And I'm going to rewrite the whole integral now in terms of theta. Integral 1 over. Okay, x squared is this thing squared. So 9 tan squared theta. And then the square root thing, I've already done all the work. This is just 3 secant theta. And do not forget the dx. That's what students forget. 3 secant squared theta d theta. Questions? Cancel some stuff. I think some good stuff happens here. Let me see. This 3 and that 3 go away at least. So I still have a 9. I can bring a 1/9 out. Okay, I lose one of the secants here, one of those. So I still have a secant on top, right? I still have a secant on top. And on the bottom, I have a tangent squared. What to do, what to do? Well, whenever I'm looking at something like that and I'm unsure what to do, I just rip everything apart. So I just put the secant over 1 and then 1 over tangent squared. What I'm gonna do is get everything in terms of sine and cosine. So secant by definition is 1 over cosine. So this is 1 over cosine theta times, and then tangent squared, right? 1 over tangent squared should be cotangent squared, but then cotangent is cosine over sine. Cotangent is cosine over sine, so I square it. So I'm going to get cosine squared theta over sine squared theta. That's what that is.
Well, we could cancel some more.
Cancel a cosine. So I've got 1/9. I've got a cosine theta on top. Ooh, I'm happy about that. And then I have a sine squared on the bottom. I'm really happy about that. Because now, oops, d theta. Because now I'm going to make a basic u sub. Do you all see the u sub?
Cosine, isn't it?
Cosine, no, cosine's on top.
No, I'm sorry. You're gonna make sine.
Sine, right? So we're just going to go sine theta is my u. The derivative of that will be cosine theta d theta, which is what's on top, right? So this must equal 1/9 integral. Okay, cosine theta d theta is the du. And the sine theta on the bottom, that's u. So this should be 1 over u squared. I'm going to write as u to the -2 right? It's not natural log. If it was 1 over u, I'd leave it as 1 over u, and then we do natural log. But because it's 1 over u squared, I'm going to bring it up as u to the -2. And that way, when I do the antiderivative, I get -1/9 u to the -1 plus c. So power rule on this. And then that's just -1 over 9 u. I'm just basically rewriting this, dropping the u back down. U was, what was u? U was
Sine.
sine theta. Okay, I realize this is like bringing everything together here, right? I mean, there's a lot happening here. Plus c. I've got my plus c here, plus c here. All right, what was sine theta? Well, don't tell me u because I just came from u, right? I don't want to go back to u. I need to figure out what sine theta is. So this is where I go back up and I try and figure out what sine theta is. And you see, Lewis, I don't have sine theta anywhere. So I've got to use a reference triangle. So I'm going to go to this piece of information right here. And from that, I create a triangle. Theta's here. That tells me that tangent theta is x over 3. Do y'all agree? Take that, solve for tan theta, divide by 3. So tan theta is x over 3, which means the opposite over the adjacent is like that, x over 3. And that forces my hypotenuse to be the square root of 9 plus x squared. Questions? And what did we want? We wanted -1 over 9 sine theta. I'm just going to keep writing here. This is going to be equal to -1 over 9 times. Now sine theta off this triangle would be opposite over hypotenuse. So x over that, right? X over the square root of all that. So x over the square root of 9 plus x squared, which because it's a fraction in the denominator could be flipped. I could do something like -9 plus x squared over 9x on the bottom. Plus c.
I thought when you flip, the 9 stays with you.
Wait, when you do what?
When you flip, I thought the 9 stays. Like, so it would be 9 times, so it would be 9x. And then when you flip, okay, sweet, never mind.
Yeah, if you put that 9 up here with this like that, then you basically have like 1 over a fraction. So the fraction just flips over. And you get this. I don't know who said that. Was it Ricardo? Who was that?
No, that was me. I
Oh,
just,
okay.
I made a mistake. That was my bad.
What do y'all think?
I like it.
Yeah, it's interesting.
Really, yeah, it's really cool.
Yeah.
It's one of those ones where I definitely understand why you say it's the hardest, but it's one of those things where it's like every individual thing we're doing isn't that hard, but each problem is going to suck.
Yeah, these problems are long.
Because
So
it's
check
like,
this
yeah,
out.
that is one hard problem, but each individual thing is very reasonable.
Let's appreciate just what we've done here, okay? Let's take the derivative. Let's take the derivative of this. Okay, let's go back to Cal 1, check our work. I'm gonna take derivative of this and I better get this answer, right? I better get this as an answer. Okay, here we go. I'm gonna work this fast. I'm taking derivative of a quotient, so I have to do the quotient rule. So I do derivative of the top first. So the negative is gonna come with me. The derivative of the square root of something is 1 over 2 square roots of that something times the derivative of what's inside, which is just 2x. Okay, that's derivative top, times the bottom, 9x, minus the derivative of the bottom, which is just 9, times the top, which is negative square root of 9 plus x squared. All of that over the bottom squared. If you follow, yes, yes, am I on the right track here? Let me start cleaning some shit up here. These twos cancel. Let's see, this minus and minus become a plus. So I have negative 9x, that's basically x squared, sorry. That's me putting this x, 9 and x together with a negative, and then over the square root thing on the bottom. And then I have plus, and then over here, I have the 9 in front of that, so 9 square root of 9 plus x squared, and then the whole thing is over 81x squared. I'm gonna get a common denominator. In the numerator, I'm gonna put these two together, which means I need to put a root down here on the bottom, root 9 plus x squared there, and then I have to multiply top by the same thing, 9 plus x squared like that. That will give me a new fraction with the square root of 9 plus x squared on the bottom. On the top, let's see what we get. We've got the minus 9x squared. And then when we put these two together, the root goes away and we had a 9 in front of it. So it's plus 9 in front of 9 plus x squared. And then all of that's over 81x squared. Oh, I forgot the parentheses here. Let's distribute here and here. So we have minus 9x squared plus 81 plus 9x squared. That's my new numerator. I'm gonna have to come over here. Here's where we are. These cancel. So I have 81, right? That's what, all of this crap becomes 81 over the square root of 9 plus x squared, and then all of that over 81 x squared over 1. You could look at it like that. And then when you flip and do the multiplication of the reciprocal, you get the 81s to go away, and you get it. Yeah, all right. How are we doing here, time-wise? Maybe time for one more? First step for this, after you realize you're going to have to use trig sub probably, is to rewrite it like this. We realize that raising something to the 3/2 is the same as taking the square root of it and then cubing it, right? Now, tricky part to this problem right here. The formulas we have, that there's 3 of them, that they deal with when you have the square root of a squared minus x squared. Notice the coefficient on x here is 1, right? And then same thing with this one, square root of a squared plus x squared, it's 1x squared. Here, it's 1x squared, right? I've only shown you 2 of these. There's a third one, right? We haven't done yet. We've done it where you replace it with a sine theta. We've done where you do a tan theta. We have not done one yet where we do a secant theta. We will, just not today. So right now, when you look at this, do y'all see we don't have a 1 in front of x squared? Right? We don't have a 1 here. So first thing I'm going to do is I'm going to factor a 1 out. I'm going to factor out what I need to make that a 1. So I want you to focus all of your attention right now, before we get started with this, on 4x squared plus 9 underneath the root. I'm going to factor a 4 out from the x squared, which means that the 9 turns into a 9/4. Right? We can always pull numbers out like that, because if I distribute this 4 back through, I will get, in fact, 9 here. And now I can take the square root of 4 and come out of the radical as a 2. And now I have x squared plus 9/4. Agreed? It's just algebra. But remember, in the problem, aren't we cubing all of this? Right? We're going to cube all this. So imagine that this was all cubed. This was all cubed. This was all cubed. I would have to cube that too, wouldn't I? So this is really 8 times, and then this thing being cubed. Y'all with me on that algebra? My next line, watch my next line. 1/8 integral x cubed over square root of x squared plus 9/4, all of that cubed dx. So basically what I did is I took that whole denominator where we pulled that 4 out as a 2, cubed it as an 8. Because it was in the denominator, I pulled it out as a 1/8 in front of the integral. Now I can play my game because I've got this square root of x squared plus a squared, right? X squared plus a squared, which means we can play the same game we just did in the previous one, right? Wasn't this how we handled? This is how we handled something. We have x squared plus a squared. Remember with the plus, the order doesn't matter, right? A squared plus x squared plus a squared, same thing. So my question now is, what's a?
A is now 9/4. Well, actually, no, it has to be squared. So
Square root of.
Square root of the
3/2.
9/4. 3/2. 3/2.
Professor, I have a question. Instead of, let's say in this case, we took out a 1/8 because 4 was so nice instead of the square root, we can take that out. If we have, let's say, a 3 inside of the square root, isn't it the same thing, the same, like the square root of 3 times the square root of x squared plus whatever we get out of? Like we can still.
Yeah,
take
so
out the
like,
square
let's
root.
say that this was the 3 here, right? Then what we would pull out to the outside would be square root of 3. And then we would cube the square root of 3, and that would come out. So I'd probably on the outside have 1 over the square root of 3 cubed. That would be my constant on the outside. Which is, look, that is well within the realm of this class in homework problems. We're doing nice numbers right now. This is the first problem. We're going to have a fraction for a, okay? But you can have things that are like irrational numbers, like square root of 3. So good question. Okay, so y'all said a was what, 3/2? 3/2. So here comes my trig sub. I'm going to do this trig sub right here because this is the form I have. So I'm going to replace x with 3/2 tan theta. When I take the derivative of that, I get 3/2 secant squared theta d theta. Don't forget the d theta when you do your derivative. And I also know that the square root of x squared plus 9/4, I know that if I work this all out, right? If I replace the x and did all this crap in here, I know automatically it turns into a secant theta. So this will be 3/2 secant theta every time. So these are like the 3 things I need to proceed with the problem. Questions? Take
On
a
a
moment.
test,
Pardon?
on a test, if we were to write like the formula next to it, would that be substantial, or would you want us to work it out on the test?
Oh, you mean, do you have to actually, like in the previous problem, I actually derived exactly what this turns into, and then turns into 3 secant theta. You're saying on the test,
Yeah.
you just use the formula. I am perfectly fine with you just using the formula.
Gotcha. Do you want us to like mention that we use the formula, like write the formula next to it and then go past that and input the A's and the X's?
You don't need to. I mean, you can mention it. It's fine. I mean, just make sure that you are doing the right thing. You know, don't accidentally use the one for one of the other 2, because there's 3 different things that could happen here.
Yeah. Okay.
Okay, you go now, right now, and see if you can rewrite this integral. I'm going to give you like 3 minutes, 4 minutes, see if you can rewrite it. Once you rewrite it, see if you can figure out how you're gonna go about solving it. While y'all are working it out, I'm gonna work it out myself, and I'm just gonna silently do it. Y'all want to talk about that?
Yes.
Okay, so
Shoot.
any confusion on anything? Did I mess something up?
Shouldn't that cosine from the secant be on top, not on bottom?
Cosine, oh yeah, hold on. Let me see, hold on, that's 1 over cosine.
Yeah, but it's also then,
Yeah, yeah, it's the reciprocal.
I thought you take
So-
out the tangent, a tangent, and then do a trig identity, and then find the derivative of secant, which includes tangents.
See, this is, hold on, this is cosine cubed, this is 1, no, hold on, 1 over cosine theta. Yeah, no, it's gonna come up top, right? This is gonna come up top and kill off one of the cosines on the bottom, so you'll have cosine squared. Good job, Hunter. All right, so what, okay, so who was saying what? Someone was saying something else? Bruce?
That was me. I thought you were gonna take out a tangent, make a trig identity with secant, and then find the derivative that includes tangent.
Got you. Okay, so on our methods, do we have something that deals with tangent to an odd? If you have tangent to an odd, it says to pull out a secant and a tangent. Right? We pull out a secant and a tangent, and unfortunately, we don't have a secant on top. Right? So we could peel a tangent off top, but we don't have a secant to pull. You can't pull the secant from the bottom. The secant's on the bottom, so it has to stay there. So our only hope is really to switch it over to this. Sine and cosine, but does this help? Do we get anywhere here? You want to see what we can do, or?
Can you pull out a sign?
Okay, pull out sine, let's do that. No questions on the constants, 3/16. Everyone's all right with that?
good to me.
No. Pull out a sine. And now make a u sub, right? The u will be
Cosine?
cosine. Because the derivative of that's negative sine, and we almost have that. I will need to multiply both sides by -1 to make that a plus so that they match. And now we get everything in terms of cosine. Right, everything in terms of cosine now. So I'm going to need to use Pythagorean in the numerator to write that as 1 minus cosine squared theta. And so my new integral is 3/16 integral 1 minus u squared over u squared. Come on, over u squared times negative du. I've got 7 minutes. I think I can finish it. Come on, any questions?
No, it's making sense.
Everything good? Okay, I'm gonna do something a little different than I did on the previous one. I'm not gonna pull that negative out. I'm gonna leave it there. I'm gonna rewrite this. Notice I have 2 terms in the numerator, 1 in the denominator. I can split it up. I can write it as 1 over u squared minus 1. And then negative du times negative du. I'm going to distribute the negative through the parentheses here. It's going to turn the -1 to a +1. It's going to turn the 1 over u squared into a -1 over u squared. So it'll look like this: 3/16 integral, watch, 1 minus u to the -2 du. So that negative went in here, turn that into a +1. So I put it here. Turn this into a negative or a -1 over u squared. So I did minus, and instead of 1 over u squared, I wrote u to the -2 because I need a power rule. Are y'all feeling ill yet, or you okay? It's like a
Interesting.
giant freaking puzzle.
Yeah,
All right, so here we go. 3/16. All right, antiderivative time. Carefully. What's the antiderivative of 1?
you.
U, right? Our variable here is u, so it's going to be u. And then minus, that's just 1 over u, but the negative comes out, so it turns into a +1 over u. I'm just trusting you can do the power rule on this, right? Add 1 to the power, scale it. So that gives me that plus c. So I've taken the antiderivative. Now let me go back. This is 3/16. U is cosine theta. That was the substitution we made. And 1 over cosine theta is secant theta. plus C. We're almost there. Almost there. Okay, we need to go back and figure out what cosine theta and secant theta are. I go all the way back to my trig sub. Here was my trig sub right here. Right there. I'm going to take that
Professor,
right
is it
there.
possible to do an early trig sub?
Oh, that you would need another trig sub?
Yeah, like for example, just do like your identity is already set. Like before everything's still in the finish line, you just insert your things.
Oh, you mean like when you do this, go ahead and do the triangle early in the problem? Oh, yeah, you can do that. All right, so here we go. We got this, we got theta. Now be careful, look at this right here. This is the first time we've seen this with a fraction here. Watch the way I rewrite this. I'm going to rewrite this as 2x over 3 is tangent theta. So I multiply both sides by 2 and I divide both sides by 3. That way I get a ratio on the left side. And that means when I look at tangent as being opposite over adjacent, I got 2x over 3, or 2x here and 3 here. And then that forces this side to be square root of 4x squared plus 9. Okay, that should look familiar. Does that look familiar? All right, we're there. 3/16 cosine of theta is adjacent over hypotenuse, so 3 over the square root of 4x squared plus 9, and then plus secant, which is the reciprocal of this, right? So it's just this thing flipped over. Over 3 plus C. There it is. That's the antiderivative. Let me grab my textbook real quick. One through 61 all, or wait, 326, yeah. 61. So I think right now, the only one we haven't done, the only one I haven't shown you is when we have, wait, hold on. Did we do this one? Wait a minute, which one did we just do?
I thought it was the a squared plus x squared, isn't it?
Yes. Hold on. We did this one, right? And then before that, we did the a squared minus x squared, right? So we just haven't done x squared minus a squared. So on your homework, basically for this section, everything's on the table except where you would have an x squared minus a squared. So these are the ones you can't, well, you could try them. I just haven't shown you the trig sub yet, you know, but if you look at what the trig sub is, you could go try them. Problems like number 43, 46, 51. 54, 55, and 61. Those I would skip right now. Okay. The assignment is 1 through 61 all for 6.2. Those I would stay away from at this time. All right, because we just haven't done them. And there are some things that could pop up. Now, I'm going to warn you ahead of time. There are some scenarios that I haven't covered yet that could come up within these problems. And I'll give you, I know we're out of time, but I'll just give you an idea of what I'm talking about. It is possible. Let's just look at this one right here. Okay, let's just say that we were here and say within this integral, where would it be? Think here of how this, yeah, you know what? It is possible, and I'll show you next class. It is possible that when you do your antiderivative, you work through this integral and you get here, and at the end, you might have like cosine theta, right, which you do your reference triangle for. And then you might have theta show up to just theta, not sine theta, cosine theta, tangent theta, just theta show up. And if just theta shows up, then you go up to your trig sub, and you know, like on the last one, we had 2x/3 is tangent theta, right? We had that. What you do is just take inverse tangent on both sides. And if you do that, you get an equation for theta, and that's what theta becomes. Theta is the inverse tangent of 2x/3, and you're done. Like there's nothing else to do. Okay. You also might need double angle identities, the half angle identity. So just be aware, if you get in the homework and you start seeing stuff I haven't done in class, I am going to do those next time. All right. Y'all have a good one. We'll see you on Wednesday.
Sir, I have a quick question, just kind of
Yeah.
about the homework, specifically the homework from last week.
Uh-huh.
So I turned it in, but I really wasn't able to get a whole lot done. And I'm just curious,